going to look at a particular type of control chart here, and this is based on attribute data, more specifically proportion kind of data, so proportion defective. So let's take a look at it from the point of view of an example and see what we can do with it. Right. So we have a car parts supplier who is testing weekly samples of 15 subassemblies. So the sample size is 15. These subassemblies are taken from the assembly line, and these are taken over 10 weeks. The inspector records the number of defective subassemblies. So what is the inspector doing? Looks at these 15 subassemblies every week and puts them in two different categories. Something that is defective and something that is not defective. So you have a truck door that's defective, a truck door that's not defective. It can be one or the other, right? The inspector does not care about the extent of defects. So a little scratch on a door versus a door that is has a much higher degree of defect is treated the same. They're both called defective regardless of the extent of defect. So if that's what you care, that's all that you care about is looking at defective versus non-defect, this is the kind of chart that would be appropriate. Coming back to the data, so they're over 10 weeks getting samples of 15 each. The data that we have is described to over here. So week 1 through week 10, each week 15 doors are taken, 15 subassemblies of doors are taken, and the number of defective ones are being recorded. You can total these up and you'll see that there are total of 12 defective subassemblies, and so these are out of a total of 10 times 15, 150. So that's the kind of data that we have to start off with. Right. So we're moving towards calibrating a control chart. So let's do the numbers here and see what we can find. So first thing, we want to get an average proportion of all the proportions that we saw over here. We had 10 samples of each of size 15. Each of the number of defects in those samples can be converted into a proportion. Each one divided by 15 is going to give us a proportion. And then we're also going to get, for purposes of constructing the control chart, the standard deviation. The reason we need to get that is because the upper and lower control limits are based on plus or minus 3 standard deviations. The formula that you see over here is basically telling us how do you get the upper and lower control limits. So it's the mean plus or minus 3 times the standard deviation. The standard deviation is computed as whatever proportion you got as the average proportion, multiply that by 1 minus the average proportion and divide that by the sample size, all under square root. Right? The sample size here, this is something that you need to pay close attention to. The sample size is 15. Right? It's 10 samples of size 15. So the sample size here is a constant 15. That's what you'll be using to compute the standard deviation here. All right, so let's go through some of these computations here. So in order to get the average proportion over those 10 samples, you can do it 2 ways. You can either take each of the proportions. So the first sample had 3 defective subassemblies out of 15, giving us 0.2. Second one had 1 out of 15, giving us 0.067. Or you can simply take the total 12 defective subassemblies over the 15 samples, over the 10 samples of size 15. So you're going to get 12 divided by 150, and that will give you the average. Right? So either way, you're going to get an average that you'll use for the center line. And if you were to take the other method, which is taking each of the proportions and averaging them out, you would get the same thing. So here you have each of the proportions shown to you for each of the samples. If you calculate the center line for this, it's based on 12 divided by 150, which is 0.08. And the standard deviation is based on 0.08 times 1 minus 0.08 divided by 15, which is the sample size, all taken under square root. So the standard deviation works out to 0.07. The upper and lower control limits are simply computed based on plus or minus 3 standard deviations. Now, the point that you might want to note here is that the lower control limit actually turned out, based on the computation, strictly based on the computation, it turned out to be negative 0.13. Now, as you know, negative proportions are not going to make sense. There are no negative proportions, so we're going to bump that up to a 0. So the lower control limit is going to get bumped up to a 0. What this should also tell you, something that you might want to note, is that this chart is not going to be symmetrical, right? You're keeping the mean at 0.08. The upper control limit is at 0.29 based on these calculations, and the lower control limit is now going to be 0. So it's going to be an asymmetrical kind of control chart, that's what we can see in terms of the chart. And here I have the chart generated based from Minitab software shown to you over here. So now it's time to interpret this control chart. What do we see here? We see that there is a point that's marked in red that's outside of the control limit. This is the 8 defective subassemblies out of 15 that was found in that one particular sample. So if you go back to the data over here, you can see that sample number 8 had 5 defective subassemblies, which gave us 0.333. So staying on this slide, you can see that there's going to be a problem because 0.333 is above the upper control limit, which is also what is shown to us in this picture, right? That there's a point outside of the upper control limit. The question that you should be asking is, so what? What do we do next? We found a point that's outside of the control limit. Well, it's going to depend on whether you're trying to calibrate the chart at this stage or not. And here it's clear that we're trying to calibrate the control chart. We're using data from the process to come up with the upper and lower control limits. So what do you need to do? You need to figure out what happened at that week 8. There was a proportion defective that was higher than the upper control limit. Can we figure out what the reason was for that? If it is reasonably clear, if it's clearly a special cause variation, something that should not be impacting the process on a day-to-day basis, then we can simply delete that sample and we can recompute the control limits. So we throw out that sample and we recompute the control limits based on not having that sample in our calculations. If that's not the case, if you cannot really eliminate that particular observation, that particular sample based on a cause that's clear, then you have to go back to the drawing board and recompute the control limits. So let's take the easy route here, and let's say that we could figure out the reason for week 8 proportion being outside of the control limits. So eliminate that point, and then you go in and you figure out the new control limits. Right. So here you see that there's no week 8 being represented here. You're going from 7 to 9 and 10, and because you've thrown out week 8, you've got the same data that you had earlier. You come up with a new mean proportion, which is going to be based on now. What was it? We had 12 defects earlier. We took out the one that had 5, so we have 7 defects out of a total of now 135. So 7 out of 135. Gives us a mean proportion of 0.052, and then you get the standard deviation based on that, and then you get the upper and the lower control limits based on that. Now, what you can see from here, based on the proportions that you have for each of the samples, as well as the upper and lower control limits that we've already computed, you can see that there's going to be no problem in terms of points outside the control limit. All the points are going to be within the control limits based on the fact that we can see based on this data. Plotting it in terms of a chart, you can see the same result. You can see that all the points are within the control limits. So what you can say from this, what you can infer from this, is that the current process is expected to have between a 0 to 22% defect rate. We got the 22% defect rate based on the upper control limit. So given the current technology, given the way the process is designed, given the kinds of training that you have for your people, you are expecting a 0 to 22% defect rate from this particular process, right? Based on what your context is, it may not be appropriate for you to use just 10 samples that we used over here in order to compute the upper and lower control limits. So even moving beyond this particular problem, you might want to reflect on the fact that was 10 samples enough for you to come up with the upper and lower control limit. And that's going to be context dependent in the sense that what are the different types of things you want to cover in the number of samples. If it's many shifts in the day, many samples during many shifts in the day, many days of the week, then obviously you have to have coverage for those sorts of things in your data collection. So then I would have samples that are collected over a couple of weeks to make sure that every day of the week is represented at least twice, and then if there are multiple shifts, they are being represented in the sampling that is being used to come up with the inherent capability of the process. You also want to think about whether you want to separate different days, separate different shifts, and those are the kinds of managerial decisions that you will need to make in addition to the mechanics of computing these control charts. So finally, when and how do you use the control chart, the P chart, the proportion control chart? You use it to compute control limits for attribute kind of data. It's a discrete distribution. It's data that's dealing with conforming and non-conforming items. Right? All it's telling you is whether there was a product that was defective or non-defective, or it was defective or as expected. You may use different subgroup sizes in order to come up with the process with an attribute kind of control chart, with a P chart. What do I mean by that? Well, we used sample sizes of 15. It was a constant sample size across. It's possible for you to construct a P chart based on having different sample sizes for each of those samples. We simply haven't gone through those kinds of calculations, but you can find those in software. You can find those in different sources to be able to compute control charts for different sizes of samples. Recall that you're only dealing with two possible outcomes. So this is based on, if you're familiar with the binary distribution, the binomial distribution rather, you're talking about a binary decision, a binomial distribution saying something is either good or bad. It's a 0-1 kind of decision. You want the subgroup size to be large enough to be able to capture defects. If you're finding a lot of zeros, then your subgroup size is not large enough. So you want to think about that. And then in terms of the frequency of how you collect data, whether it should be every hour or once every day, that's something that you also have to think about in terms of designing this system of assessing your process over a longer period of time.